So first, thanks to the organizers to give me the opportunity to present my results. And I hope this talk will bridge with the first two talks of this morning, because it's an experimental talk with some experimental method that might be useful for cells, even if I'm not using that for cells. And so this work is here. Yes, this talk is mostly the work of the PhD of Singh. I'll be talking about gels. So gels, we've heard a bit about that. They are everywhere. They are in our food. They are in our body. They are also in some of construction materials. And they are characterized by a microstructure that is a network that is, let's say, solid, and that is interpenetrated by a fluid. And you can have that made of very different building blocks at different scales. And so I would argue that is the definition of gel, not the mechanical behavior. You can have very different mechanical behavior out of the microstructure I just told you about. For instance, if this microstructure is just limited to a few microns, let's say, you call that a microgel, and if you jam those microgel together, then you will get what is called a soft glass urology. You'll have a yield stress fluid that is typically the hand gels that we are all using for a few years now. If now you've got a reversibly yielding gel, so like, for example, what Safar talked 2 days ago or Paddy yesterday, then if you have those colloidal gels that with particles that attract each other rather weakly and reversibly, and being able to roll on each other and this kind of thing, then you've got actually the same kind of rheology. You have some differences, but at least you've got something that is reversible. You can shear your system, wait, do it again, and well, if you do that often, you will get the same kind of result. But what I want to talk about are those irreversibly failing gels that are really not, I would say, not complex fluids, but rather soft solids that will actually fracture irreversibly. And I think the irreversibility part was what was really important in Suzanne's talk yesterday. And so why would we need such soft solids? I will just give you an example. As a structural material, you would need that, for example, in your body if you wanted to replace cartilage, let's say. So this is a soft part of your body, rather soft. You want to have something that is mostly as soft as this, otherwise your body will react in a different way. Also, you will need low friction, and the gels have usually very low friction. But there is something that gels do not provide yet. There must be long lasting. I mean, if you have a surgery to implant something in your body, you want that to last more than just a few weeks, right? A few years would be better. And if you want to be in par with current prostheses that are made of ceramics, you need to last at least 15 years. And for that, you need some fracture resilience. And when I talk about fracture resilience, that's not being run over by a truck. I mean, if you're run over by a truck, the fact that your heat replacement is broken is probably the least of your concern, right? What you want is more like this gentleman being able to run every weekend for the rest of your life, right? So that's a lot of rather low stresses, but repeated, or that you just standing, for example, is a stress that you have on your joint, and this will be sustained over the rest of your life. And so our issue is subcritical failure. That is it's not breaking immediately, that might be breaking after a very long time. And the issue with those kind of failure is that, as we say in French, so a quarter an hour before his death, he was still alive. means that if you go to the medical doctor just a week before your injury, the medical doctor will say, yeah, your knee is fine, there is no issue. Microscopically, there is no issue. Maybe if you had a scanner that day, maybe you would see something, but just microscopically, everything is fine. You have no special pain or whatever, but a week later, your knee you have a knee injury, and it means that in a somehow invisible way, the material is accumulating some damage. And the question I want to ask here is, what is damage? And how can we characterize it? How can we know how a gel here accumulates damage? So very generally, in brittle solids, you can construct this kind of curve. So you apply a stress on a pristine material, and you wait until it breaks. And then you can construct this curve where you have the stress here and the time it took for it to break. And you can do that for many different stresses, and you can construct this curve like that. Once you have it, you may wonder, well, what will come out if in a more complicated stress history? So let's say you're a nasty scientist, I mean, borderline evil scientist, and you know that your colleague will be testing a sample tomorrow. You take the sample out of the shelf. This is a pristine new sample. You put that in your testing machine, and you apply a stress on it for, let's say, 1 hour. It doesn't break. You put it back on the shelf. You tell nobody. Then your colleague comes the next day, take the same sample, put it, and it breaks in 1 hour. But it's at odds with all of our previous results, because you would say, oh, but this gel, this material, I mean, according to previous experiment, would have broken in 2 hours. Why did it break in 1? Well, because you have an evil colleague nearby. And more generally, if you apply a different stress history on that, on material, you can just sum up those ratios of the time over which you apply the stress by the failure time you would have on a pristine material at the same stress. And if you sum up those ratios like that, that would go, and if it goes to 1, then you get failure, right? I spent like half of the time of the lifetime of the sample of my colleague. So when she measured the next day, this will break in half of the time it would have needed to break it, right? And that tells us that the damage resistance is actually independent of history. I mean, if the material has already, the damage resistance is somehow given by this, so by that curve, if you want, and it doesn't matter that the material has done something else before if you know the whole history, right? But the issue is that most of the time in engineering, we don't know the history of the material. We don't know exactly what was the force on this landing gear. We don't know if you were running with a very heavy backpack a few months before you had your knee injury and this kind of things. So most of the time, in industrial context, you retire your mechanical part. If it's critical, you retire it way before the lifetime you have probably computed, just in case there was at one point one stress that was larger, or you applied for quite longer than when you thought, or something like this. And so that costs a lot of money, right? But this is industrial context. This law, this Bailey criterions here, has been very well verified by Casein and co-workers on Casein gels, and that's the system I'll be talking about. So you already saw part of that experiment yesterday in Susan's talk. So here we are basically shearing yogurt. But don't think about the steered yogurt that is a kind of complex fluid, but rather the solid yogurt you just get if you don't steer anything and you just get the thing after gelation, right? So it's a soft solid, a bit like a jelly. And we put that between two concentric cylinders. That's a quet cell. So we are applying a torque on the inner cylinder, and we are, it's a constant torque. So that's the same experiment as this. And we're looking from the side here. And we also record the strain rate at which the material will deform. And for a long time, we just observed this power law creep here. And there is absolutely nothing to see from the outside. And at some point, we see a crack appearing here. And if you see well, you also have some cracks appearing down there. And that's actually when our curve will turn up like this, and then it's only fractal growth and the material will break. But that's not the regime I'm interested in. I'm interested in this part, where the material is probably accumulating damage. And is it possible, even if we don't see anything microscopically, that there is something happening, and can we actually detect the damage that is occurring there? For the detection, the answer is yes, and that's not because of me, that's because of Stefano, Laurence, and Luca Cipelletti, who looked at coupled rheology and light scattering. And same kind of experiment. So this curve, this red curve, is more or less the same one as what I showed you before. And those blue curves are a measure of the local non-affine dynamics in the sample. And we see that this non-local dynamics has a big burst here when you have, just when you're near this minimum and you have fracture nucleation. And so they call that dynamic precursors, of course, because what they measure is the dynamics. But my question now will be, what are the microstructural changes that are associated with this burst in dynamics? Can we actually visualize this? And so here is the issue there. We want rapid 3D visualization of what is going on in the sample. The sample is inherently 3D, so we really need 3D visualization. And it needs to be fast, so we'll use confocal microscopy. But confocal microscopy is an optical technique, and it's limited by diffraction. So basically, anything that is smaller than 300 nanometers, we won't be able to distinguish. So we need large microstructures, say something north of 1 micron, to be able to visualize anything. But if you have a large microstructure, scaling mules would tell you that you will have very soft materials. It means something like 1 Pascal in moduli. So that's very soft. And on that, you want to apply stresses, and you want to apply reliably stresses that are much lower than this, so because you want to be subcritical, right? So the kind of resolution you need in the stress you apply is about 1 millipascal. Good rheometers can do that. But if you do that in a rheometer, they will do that on tens of centimeters square areas. The issue is, if you want to know what is the relationship between the damage you would observe and the nucleation of fractures, if the fracture is nucleating somewhere in your centimeter square bulk, and you're looking just on the millimeter square, that's basically the scope of your microscope, then, well, you'll have to do 10,000 experiments before you observe actually something going on where you're looking at. So we will need to focus the stress on this 1 millimeter square so that we actually observe something quite often. And this means that the kind of forces we need to apply are much lower than what a rheometer can do. It's about the nanonewton. good luck, I was told, but we managed to do that. So the idea is, so the sample is, here is the pink part. It's between a cover slip here through which we can look with a microscope and the head of a cantilever. And don't imagine an AFM. This is 20 centimeters long, right? Then if with sensors here, and I say sensors with a plural because I have two like that in the shear plane, I can detect the position of the head with respect to its base. So basically I have the deflection of the cantilever, and so I can get to a force and then to the stress. And because all this rigid mechanical part is mounted on micromanipulator, if I sum the displacement of the micromanipulator with the deflection of the cantilever, then I have the strain basically on my sample. Oh, and by the way, giving back to Caesar what belongs to Caesar, the original idea of that was from Hélène. And we got, and so with this, the kind of experiment we'll be able to do is to, to apply a constant shear, shear stress and control the gap normally. And so we are in the mixed mode where one part is, we have the control of the stress in the shear direction and control on the strain in the normal direction. But we can get then the normal stress and the shear strain like that. Oh, but that's not all. Maybe you have noticed here that you have a triple line. Here it's a point, but a line between air, a solid, and the gel, which is mostly water. So this will be, I mean, this is just terrible because you'll have triple line anchorage there. And basically those interfacial forces that you'll get there will completely dominate the kind of measurement you would be doing. So we immerse everything. And to be quick, I would say we immerse everything in the same solvent as permeating the gel. That's a bit more complicated than this, but here we are.
So how is the stress, shear stress controlled?
So basically by feedback loop. We are neither stress control nor strain control. We're somewhere in between. But so we need feedback loops on any of the thing we want. So we can choose to have stress control in shear and strain control in the normal direction. That's what we do, everything that we'll show you. But we can have all the choices if we want.
So just like a rheometer, basically, in that sense.
Rheometer usually is either stress control or strain control. At least that's what they sell you.
Yeah. But so here you can go better resolution in torque. Is that the idea?
So so it won't be a torque.
Yeah,
it will be but the resolution in stress will be more or less the same as in the rheometer, but applied on a much smaller area. And this much smaller area corresponds to where we are looking at. So the stress is not distributed over a large sample that may break somewhere I'm not looking at.
Okay, sure.
And so this is what it looks like in reality. So the cantilever is the copper wire you might be able to see here, so 20 centimeters long, as I said. And this big beam here is just the support for the sensors. And we get a resolution of around 6 millipascals for that, which is, well, okay, like a rheometer, and 0.1% resolution in the in strain. And so the system, very briefly, we are using yogurt, so it's proteins, it's milk protein in water, and we acidify those proteins, this solution, using this molecule, so that the proteins go from being negatively charged at neutral pH to globally neutral at a pH around 4.5, and then the aggregate. And that's exactly what happens in the yogurt you're eating every day. Not with this molecule, but that's all right. And we also put a little bit of fluorescent dye to be able to see things with the confocal microscope. And here are the images you can get. So here the bright parts are where you have protein, so that's the protein network. And the dark part is where you only have solvent. And this is one slice we can get, but because we can construct a pile of a stack of those slices, then we can reconstruct the orthogonal projections like this, and orthogonal cuts, sorry. And you can recognize here that here we have the head, you see a little curvature, and the cover slip is here at the bottom of the image, and the head will be moving in that direction, so we'll have a shear a bit like this. And so no, the screen is not broken. What I'm just doing here is that superimposing the time t as a magenta image and time t+1 as a green image. And so when they superimpose, it's gray, like you see at the bottom. And when they do not superimpose, you see those kind of stripes like that. If you continue shearing, then you observe that the pores, maybe if I can come back, it will be more obvious, but the pores are growing. At some point, especially if you look around there, you have a big pore like that. You have another one here. Maybe they are connected out of plane. And then you'll, once it has touched the head here, it will just propagate along the head. And you get, actually, that's fractures. And so we are able to see those fracture growth and things like this. And the failure. But what I'm interested in is this diffuse damage regime. So for that, I will show you another experimental picture where there is one diffuse damage event. Are you able to see it? I mean, hint, it's where the cross is. What I want to stress here is that all the rest is completely gray, meaning there is seemingly nothing happening in all the rest of the volume that we're looking at. But if we zoom and we remove the cross, if we just look in that region, then you'll be able to see that that strand got, pulled apart like this. So this you would expect because you're in the shear plane there. So you're in the shear plane, so you actually expect that things will be pulled in the shear plane and probably in this maximum elongation axis of the shear. But what is not completely trivial is that if you look in perpendicular planes, you see actually all the displacement that are out of the shear plane, meaning that you have a coupling between the local geometry, the local topology of the gel, the local anisotropy of the gel, and the release, the way the strand will move once it's broken. All right, so that was not completely expected. And well, but something that once you've got one of those, and Akash found it by hand, by the way. Now that you know that would look like, then you can do something more automatic. And we use 3D optical flow in order to get the local maxima of non-affine displacement, which is very much like what was done in Montpellier with the line scattering. And we can now count those events, and we see that the cumulative number of events is really shooting up when the material gets broken. And what is nice is we also have the pictures of what is the microstructure and the way those the microstructural change happen during those events. Yes?
The cumulative events on a linear scale and the strain on the log scale. If you put the cumulative events on a log scale as well, does it follow the same slope as the strain?
Good question. Maybe, and maybe with the movie I will show you the next slide, I would say it's not completely relevant.
Okay.
Because if yes, the movie. So you might see, so here already we're a bit late, let's say, the movie, and you see that all the stress is more or less in the same region. All those events are occurring in the same region. But when the movie will loop, you'll see that there were first a lot of those events everywhere, but at some point, this damage gets localized there, and if you look on the pictures, you'll see that's exactly where the fracture is actually growing. So it seems that we have a phenomenology where you have first discrete and somehow unrelated, I would say just somehow unrelated at the moment, events occurring there, and at some point, they become very correlated and occurring more or less at the same place, and that's where you have the fracture growth going. I would really be happy to go further on these questions because, well, the issue is that the funding ran out. And so we just managed to build the machine. We now know that, I mean, we are able to see those microstructural change, and we're able to relate microstructural changes to damage. We know what the damage look like now. We can quantify them. We would be able to do that if we had more time to actually perform the experiments. Because there are a lot of things to do with that, and that's more or less what I want to convince you about it, is that some of the questions I have on the top of my head would be, okay, is there a spatial temporal correlation between those damage events? Can we characterize the microstructure where, and compare the microstructure where the events occurred and where, with respect to other places in the gel, and why, and then understand a bit why the damage occurred there, which might be nice to actually, if you want, design gels for better resilience or these kind of things. I mean, can we use the kind of topology that observable that Safar defined 2 days ago about this in-betweenness centrality, for example? Is it important there, or is it more something more geometric about the orientation, the local orientation of the microstructure with respect to the elongation of principal elongation axis of that? So that's a lot of questions I would like to answer. Maybe you have plenty of those, so please, I'm open for all those questions. If we get more funding to continue this story.